And let me share my screen. All right, can you see that? Can you see my screen here? Okay, so I'm going to scroll back up to the top here. So this is the same notes from last time. I've edited them a little bit. So we've done this section on perturbation methods of boundary layer theory, and we're here on part 2 on boundary layer theory, and we're here in the middle of part B on the boundary layer equations. And this is the last new stuff I'm going to give you for the semester. So we're going to go through here. We're going to get to the comments. We probably won't get this done today, but we'll certainly finish it on Friday. And so if you, I will send an email after class today with a survey to please start putting anything you want me to look at, to talk about on Friday for the qualifier. And then I'll spend our class time the next couple days in class to talk about anything you want me to review for the qualifier. So please, please note that. Oh, real quick, I'm gonna make sure that I grab, last time we had someone show up late, so I'm gonna make sure I pop out this participants tab in the chat before we go on. In case someone comes late, let me do the chat too. All right, sorry about that. Sorry about the pause. Just wanted to make sure I don't miss somebody. All right, so boundary layer theory. So last time we talked about this idea of the boundary layer problem where you had forced convection around an object. And I said that we could have boundary layer problems that involved momentum and heat and mass transfer, but that momentum transfer was the sort of simplest problem and the foundational problem. So we started out and we laid out, you know, our idea of an object and flow around it, and we did dimensional analysis, and we showed that when we did that, we ended up with Reynolds 1 over Reynolds number in front of the viscous dissipation term. And when we have high flow rates, we have, you know, object following a terminal velocity, or, you know, a car traveling fast, that this Reynolds number is going to be high. And so we're going to end up with, you know, this is going to be a small value. And so we can do a perturbation expansion to solve it. And when we get at order 0 is Euler's equation. And that's a singular perturbation problem. And so we're going to have 2 regions. And Euler's equation is going to apply in the outer region far away, where the Reynolds number goes to 0. And we said, well, that's all fine and dandy, but we're going to have to solve the inner problem, or else we have issues, right? We're not going to be able to satisfy no slip, and that turns out to give us a 0 drag force if you follow that calculation through. So we had a little quick aside about Euler's equation and inviscid flow and irrotational flow to get Laplace equation. Then we said, okay, now let's go back and talk about the boundary layer equations, which are the inner problem. And so we're trying to find these equations that are valid in this inner region where the boundary layer is, and we have to rescale. And this was what we did, the same thing we did with singular perturbation problem before, where we you know, zoom into the inner boundary layer region, and we need to rescale using this parameter delta. And so I said, to be more specific, we're going to do a flat plate problem. So I drew a flat plate and said the outer solution here is going to be trivial, with just the velocity of u. So we did a dimensional analysis where we said u was our scale for the x velocity, but y velocity has some other scale we didn't know. The delta here was some scale we didn't know, and we scaled by the inertial scale and then the total length for x. And we plugged that into the continuity equation, and this was where we got to at the end of last time, was we plugged these scales into the continuity equation, and we found what the scale for the velocity v was, so what the y scale is, which is related to delta over L times u. So basically delta over L is going to be some small value and then multiplied by u. So, and that was required by the continuity equation. where we said, we pulled all these terms into one dimensionless group when we said that group has to be one because we don't have more degrees of freedom from our dimensional analysis. Okay, so that's where we ended up last time. And so now we're going to go on and do the X momentum equation. But I want to just pause right there as we've sort of done this quick recap and make sure we understand where we're at. So are there any questions about this, what we've done so far? Okay, great. So then let's look at the X momentum equation. Oh, I'm still in blue. Go back to black. Okay, so I'm going to shift something on my desk here. Here we go. X momentum. Okay, so the X momentum equation, if you remember, is as follows. We have rho dvx dt plus vx dvx dx plus vy dvx dy is equal to minus dp dx plus mu multiplied by the second derivative of vx with respect to x and the second derivative of vx with respect to y, close parentheses. Okay, so that's the X momentum equation from the Navier-Stokes equation. And we can simplify it a little bit. Notice this is for 2D. So for our flat plate, we're not worried about the z direction. So we've dropped those terms already. And we can also drop this one because we're steady. So we're not going to change in time. So that guy's going to go away. And we can take the same scales that we had up here above, these scales right here, and plug them into this equation right here. So let's do that. So we're going to have rho and Vx had a scale of u, Vx tilde, and then there should be u divided by L for dVx tilde dx tilde, plus, now we should have a term for, oh, we got someone in the waiting room. Let me let them in. We have this term for Vy. So we're going to have rho, and the scale for Vy, you remember, was this V, but we found what V is, which is delta over L. Well, I'll sub that in just a second. So we'll have rho Vy, so rho V, I'm going to move that down, rho V, Vy tilde, and then I had a dvx dy, so there's a u divided by delta is the length scale for y, dvx tilde dy tilde is equal to, and then I have minus dp dx, so p has a scale rho u squared, and x is the scale of L, so that'll minus be multiplied by minus dp tilde dx tilde, and I'm going to come down here for new line, plus mu. Now I have a second derivative of Vx, so that'll be u divided by L squared of d squared Vx tilde divided by x squared, plus the last one mu. Again, I have a Vx, so that'll be a u, and the y should be a delta squared in the bottom, second derivative of x with respect to y tilde squared. Okay, so that's just plugging in these terms. I could go through and solve for this and then plug them in the parentheses and pull them out. But as you see, I sort of get this shortcut where I just start to know what the scale is and pull that out of the piece. Any questions about that step right there? Okay, so let's collect the terms then. So we're going to have rho u squared divided by L, Vx tilde dVx dx, plus, and then this will be rho V u divided by delta, or let's see, I need a Vy, Vy tilde dVx dy tilde is equal to rho u squared divided by L dp tilde dx tilde plus mu u divided by L squared dvx tilde dx tilde squared. Forgot the square on that one. Oh, I got it right there. Plus mu u divided by delta squared, second derivative of vx with respect to y squared. Okay, so now I'm going to multiply by L over rho u squared and simplify each of these terms. So L over rho u squared is going to cancel that one, but I'll just go ahead and write it out. So I'm going to have vx dvx dx tilde plus, and I'll have L over rho u squared. And let me substitute, I have rho u over delta. Let me substitute for v that I found before. V was u delta over L. So let me put that in here as well. U delta divided by L. And now I'll have Vy tilde dVx dy tilde is equal to, okay, the rho u squared cancels that one. So this should just be minus dp dx plus, now I'll have the two viscous terms, L over rho u squared times mu u over L squared, second derivative of x with respect, or second derivative of v with respect to x squared, plus L over rho u squared, and now I'll have this one, mu u divided by delta squared, second derivative of vx with respect to y. Okay, so we're almost done here. So let's look at this guy. So we've got these terms to simplify, that term, and that term to simplify. So this term, I've got an L, a delta, a rho, and u squared and u squared. So that term all goes to 1. So that worked out. Then over here, I have an L and an L that cancel, and a u that cancel. So I get rho u L over mu. That's 1 over the Reynolds number with respect to L. Okay. And then this one, I get a u and a u that cancel. And if you look here, I have a rho u delta squared mu L. That looks a little bit weird, but that actually looks a lot like if I put mu over rho u L, that is the Reynolds number, and then I could multiply by an L squared divided by delta squared. That would be the same thing as that, right? Because I put a square here and now I put an L in the denominator. So this is going to be 1 over the Reynolds number L multiplied by L over delta squared. Okay, so to write that all down one more time, just to have it kind of clean, let's put it down here. I have Vx dVx dx plus Vy dVx dy, and I just realized I'm leaving all the tildes off, so let me put those on. Tilde, 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 is equal to minus dp dx plus 1 over the Reynolds number, second derivative of, hit the eraser button, Vx dx plus 1 over the Reynolds number L squared over delta squared dVx dy. Okay, so that's a lot of algebra, but it's important because now we're at the point where we can try and pick what delta should be. Okay, so if you look here, if before when we rescaled, if I had delta equals L, that's what I had before, right? I had the Reynolds number in front of this and the Reynolds number in front of that guy. And when I took the limit that the Reynolds number, if I said the Reynolds number, right, 1 over the Reynolds number of L was equal to epsilon, which is really small. So if that were really small and L were equal to delta, then those two terms would go away. So I need to pick something so that this term doesn't go away, when the Reynolds number is really small. So I need 1 over the Reynolds number L times L squared over delta squared to equal 1, right, when this one is small. So in other words, I need delta squared divided by L squared to equal the Reynolds number. Is that right? Let's see. To the minus 1, right? If I didn't screw that up because I put the delta there. Yep, like that. Okay. And, or in other words, I need delta over L to equal Reynolds number to the minus 1/2. Okay. Or if I wanted to write this in terms of epsilon, that would be epsilon to the 1/2. So if I pick delta to be epsilon to the 1/2, that will make that term 1. And when I take the limit that this goes, to 0, right? Or in other words, when I say, at order epsilon to the 0, I get the following equation then. Okay, so I get Vx dVx dx plus Vy dVx dy is equal to minus dP dx plus only this term, d second derivative of Vx dy squared. Okay, so that is called the boundary layer equation. Okay, and I can write it again with units. So if I put the units back in, the units are Vx dVx dx plus Vy dVx dy is equal to minus 1 over rho dP dx plus nu, which is mu over rho d squared Vx dy squared. Okay, so that's with units again. Okay, another thing we notice is that this tells us what the boundary layer size should be, or at least what it's proportional to. It gives us everything but a constant. It says that delta should be approximately L times the square root, or the minus square root, right? Reynolds number to the minus 1/2. Well, we can plug that in. Let's look at what that is. That's going to be L times, see, the Reynolds number is rho u L divided by mu, right? So that's that to the 1/2. So that means that the boundary layer should look like L mu divided by rho u to the 1/2. If I'm not mistaken. I make a mistake on that. I think that's right. Where did I write it? Oh, I'm missing that page. Okay. Sometimes this is written slightly differently. There's a mu over rho. So if we're going to use the kinematic viscosity, we'll have L nu over u to the 1/2. Okay. And if you go look up, that indeed is the boundary layer. I guess I should put this as proportional to instead of equals. So if you go look up the boundary layer height, the boundary layer is going to equal some constant times L nu divided by u to the 1/2. Okay, so by our dimensional analysis, we found two things. Okay, we found both the equation for the inner region. So that's what this is, the boundary layer equation, for the inner region. Okay, and we found what the boundary layer height is. Okay, so we found both of those things by doing this dimensional analysis. All right. So I think that's what I wanted to say about that piece. Are there any questions about how I got here or what this means?
What's that coefficient right before the d squared vx dy squared when we add units again?
This one right here?
Yeah.
Yeah, that's a new, sorry.
Okay,
I'm
great.
trying to make that. I don't know if that's any better. You can put a box around this guy too. Okay. So one more thing sort of to say, just as I'm glancing at my notes here. So what about Vy? How are we going to find Vy? Well, because this is just an equation for Vx. Okay, so Vy we can get from the continuity equation. Okay, so we have dvx dx plus dvy dy equals 0. And what we can do is solve for Vy by moving this over and then integrating. So Vy is going to equal minus the integral of dvx dx dy. And I think I write that right. Now I'm staring at my notes. Got a mistake in my notes somewhere. Make sure I didn't do that wrong. Yeah. All right. There's a mistake there I got to fix. I'll put a little sticky note on that. Oh, should be dvx dx. Okay. So the one last thing to say is if you go through and do the y momentum equation, what you'll find is that that doesn't tell you how to get Vy. That's why we didn't do it for that. That only tells you that dp dy has to equal 0. So that's another piece of information to know, but the y momentum equation isn't as useful as the x momentum equation. Okay, so that is the end of part B. That's the boundary layer equations. We're ready to go on to part C, which is called the Blasius solution. Solution to the boundary layer equations. Okay, so let's step back and think about this for just a second. So I'm going to put a summary of the boundary layer problem. So we have this outer problem, which we usually solve with Laplace equation, where we have the velocity is equal to the gradient of the velocity potential. And our boundary condition is usually something like, as r goes to infinity, we have v infinity out here. Okay, and then we just found for the inner problem, we just found a set of equations for this, and I guess I'll rewrite them real quick. So for the inner problem, we've got Vx, d, well, that's the worst d of all time, dvx dx plus Vy dvx dy is equal to minus 1 over rho dp dx plus new second derivative of Vx with respect to y. And we know dp dy is equal to 0. And we know that Vy is equal to minus the integral of dvx dx dy. And then we know here the boundary condition that the velocity at r is equal to 0 is equal to 0. So we know no slip basically on that surface. Okay, so those are the two problems that we have to solve. So you solve the outer problem. So if we're going to solve the boundary layer problem, what are the steps? Okay, the first step is to solve the outer problem. okay? And, use this outer boundary condition. Oops, outer boundary condition, okay? And you'll be able to find V outer in that case, okay? So you'll have some geometry that'll dictate what this is. And the second step then, you need to find dp dx using Euler's equation. Okay, remember Euler's equation was rho dv dt is equal to minus grad p. Okay, so if you take your V outer that you had and plug it in here, you can find what grad p is. Now you have dp dx. dp dx is the thing that is one of the things that couples this outer solution to the inner solution. So you don't know what dp dx is until you've solved this outer problem. Okay. And then in step 3, now you can solve the boundary layer equations. So solve the boundary layer equations, okay, or the inner, region, okay, for Vx and Vy, okay. And then the last thing is you use inner boundary condition, okay, and a matching condition with the outer solution, right, to find the constants. Okay, so those are the sort of 4 big steps to do. And we are going to solve, we're going to do an example here now. This will be our last thing we're going to do in the class. I think it's going to take some of today, and then hopefully we'll finish it up on Friday. We're going to solve the flat plate problem. Okay, so we're going to go do these 4 steps for an example of a flat plate. So are there questions about this sort of overall view? Okay, so kind of what I'm hoping you understand out of this is the big picture of what we're doing, and then where these equations come from. So I think this is really confusing in your book. Like when I go read the boundary layer stuff, they just sort of say, here are the boundary layer equations, solve these. And I think this preceding derivation is super important to be able to understand where this comes from and why, right? Like why are these the boundary layer equations, as opposed like, why did I drop some terms from Navier-Stokes and not others, right? And this is why, the whole reason we just went through.
I have a question.
Please.
For the boundary layer equations, are the equations for Vx and Vy coupled? Like you have to solve them simultaneously because it looks like there's a Vx and a Vy in both.
Yes, they are coupled. Yeah, and we'll see how we do that. So yeah, this right, there's a Vy right there, right? So you could just, one way to do this is you could just plug this integral and put it in there and have an integral differential equation. That's a real pain. So we're gonna see that Blasius came up with a clever way to rewrite this equation in a way that's a lot easier to solve than this. And that's one of the key things to learn that we have left to kind of figure out.
Right.
Good question. Other questions? Okay, so let's dive in then. So this Blasius solution, so I'm going to call this subpart 1, which I call the Blasius equation. So we're going to answer Mark's question right now. We're going to say, and we're going to start with our example, of a flat plate again. All right. Oh, I need a new page. That's why it's not scrolling down. Okay, so our flat plate, we've got here, we've got our V infinity is equal to U. Because notice that this up here, if I didn't say this, this is valid for any geometry, anything. It's not just flat plate. Okay, the derivation that we did above for the boundary layer equations, even though I used a flat plate to motivate it, is valid for any geometry. So I'm going to call this x equals 0. Out here, I'll call x equals L.
Can I ask a question on that, Dr. Tree?
Yeah, please.
When we say it's valid for any geometry, in the equation above, we have it in terms of like dx and dy.
Yeah.
You have to change those, like as we change geometries using the normal rules, or is it, do we leave the equation in that exact same form and kind of redefine our coordinate system?
Yeah, so what's going to happen is you can solve this outer one, and suppose you're doing it around a cylinder. You could solve the outer one in cylindrical coordinates, and then you have a relationship between x and r and y and whatnot. And this was maybe a subtle point that I made last time, but this equation here is valid even for cylindrical geometry, because if you go through and do this part here where we have this delta, and L is much bigger than delta, we know that it's of the size, epsilon to the 1/2 bigger. So for a large Reynolds number, delta is pretty small. And so it turns out the curvature of that surface doesn't really matter. So if you go through and do a derivation of the boundary layer equations in cylindrical coordinates, you'll end up with the same stuff. You'll end up with the same equations, even if it was in cylindrical coordinates. So you can plug it back in and get x, y, z, whatever, or x and y velocities just like you have here. And so, and I'm not going to do out that derivation, but I think I pointed out there a book by Gary Leal where he has that derivation. Right?
Okay, thank you.
So that's one of the nice things, right? So like one of the nice things about boundary layer theory is that you only have to deal with curvature on that outer length scale, right? The inner length scale, it doesn't matter. So like if you're doing an airplane wing, like if you want to look at the drag on an airfoil or whatever, right? You can solve the boundary layer equation. The boundary layer equation on the inner region is the same, regardless of how complicated your airfoil is. But then the outer region, you have to solve and do that. So, okay. So let's see, we have this, x equals L. Let me say this is our x direction here, our y direction is up. So just to kind of remind us of that. And I'm going to call the v infinity u in the flat plate problem. So let's do each of our steps here. So the first step is the outer solution. Okay, and it turns out, I think I said this before, the outer solution is super easy. It's just Vx equals u. Okay, so the outer solution is trivial to do for a flat plate, which is awesome. Vy is equal to 0 in the outer solution. So where we would have normally had to solve a whole Laplace PDE problem, we don't have to do that here. It's super easy. That's why we're going to start with this one. Okay. Because of this, then we can show, now we need to calculate the pressure gradients is what we need to do next. Pressure gradients. Okay, so in the pressure gradients, we have Euler's equation, which I'll write out, Vx dVx dx plus Vy dVx dy is equal to minus, what is it, 1 over rho dP dx. And we have the same thing for y. V x dvy dx plus vy dvy dy is equal to minus 1 over rho dp dy. Okay, these are Euler's equation, or this is Euler's equation. Okay, so so we look at this here and we say, we know that Vx is equal to u, Vy is equal to 0. So both of those are constants, right? So all the derivatives have to be 0, which means dP dx has to equal, dP dy, which has to equal 0. Okay, so in this case, we have no pressure change as we go along in the x direction. Okay, and so that simplifies our boundary layer equations. Now we know that dP dx is 0. But be careful, note that if I were to have done this, say, for a sphere or a cylinder, that wouldn't have been the case, right? And you remember this from Bernoulli's principle from fluid mechanics, right? If I'm going around a sphere, like I'm gonna, I think the pressure goes down and then it comes back up, right? And that happens in this case, or that doesn't happen on a flat plate, but that happens on curved objects. So this will be non-zero, for curved objects. So I'm going to put that, remember Bernoulli. Okay. So now we can move on to 3. So now we have the boundary layer equations. Okay, and in the boundary layer equations, I have Vx, dVx, dx plus Vy, dVx, dy is equal to nu second derivative of Vx with respect to y squared. And notice that the dpdx term that was here, right? That guy is gone now. So that one has been eliminated. So this looks kind of nice, except like Mark pointed out, we have this Vy hanging around, okay? And what do we do about this? This is actually not such an easy solution, okay? So this is definitely not trivial. Okay. Oh man, failure of the pen, right? This is actually nonlinear PDE. Okay. So it's not clear how we're going to solve such a thing. You might ask, well, how did we end up with something nonlinear when we tried to eliminate some, terms with perturbation theory? But if you go back and think about what we did earlier, maybe it'll give you a headache if I scroll all the way up here. But when we went and looked back at our original problem here, the small term wasn't in front of the nonlinear terms. It was in front of this second derivative term, right? All the nonlinear stuff is buried in here. So we didn't actually use our perturbation theory to try and get rid of the nonlinear terms. That's a bummer, but so we still have this nonlinearity that we have to deal with. So somehow we're going to have to solve that. And that ends up kind of biting us all the way through the problem. But the first thing that Blasius did is he said, well, I've got X and Y, and if I think about this problem here on the flat plate, this looks a lot like our startup of the flow of a flat plate. It's like a semi-infinite problem, right? Where I've got a boundary here and nothing above. And who remembers what the solution method we tried when we had those semi-infinite problems? What was that method called? Flip through your notes. It wasn't separation of variables. It was the other one.
Was it combination of variables?
It was combination of variables was one of the words. That's right. So it's combination of variables. And it had another name. Thanks, Andrew. The other name we called it was a similarity transform. Do you guys remember that? Okay. So he said, let's try a similarity transform. Okay. Or a combination of variables. Okay. And so remember that in similarity transforms or combination of variables, we define these new variables that are combinations, right, of y and x somehow. And so what we said is, well, let's rescale y by that delta length scale, right, by the boundary layer. So if you take y over delta and plug that in, and what should delta be? Well, we had delta of L up here that we had already solved for, right? We said delta was L nu over U. So instead of L, let's put in an X right here and make delta depend on X instead of L. And so that's what Blasius did. So he said, let's do delta of X here. I'm going to put a delta of X in front. Let's let that equal nu X over U, okay, to the 1/2. And he said, it turns out that if you throw a coefficient 2 in there, life gets a lot easier, okay, in your math. So otherwise you're going to have square roots of 2 kind of bouncing all over the place. And so you can't really know this in advance that there's a 2 here. And just like I said above, there was some constant we didn't know. But if you work your way all the way through the problem, you'll find out that there should be a 2 there to make your life easy. And so I'm going to put it in now so we don't have to carry around square roots of 2 all over the place. Okay, so you just have to trust me that that makes our life easier. Okay, and so if you think about this, this is, this looks a lot like our similarity transform we did before. And remember, we had something also that looked a lot like this, that had something to the 1/2, right? So what we're going to do then is take this and substitute it into our equation up here and rearrange and find a new equation to solve based on what we've plugged in here. And hopefully we'll get rid of this X and Y problem, right? And end up with something that's just some, ODE that's a function of eta instead of a PDE that's a function of X and Y, right? That's the point of combination of variables. This eta is like the worst eta. Function of eta. I don't know if that was any better, but we'll try one more time. All right. Okay. So, and we don't have time to do that whole thing today, so we'll save that for next time. But I am going to do a quick aside to address the Vx, Vy problem. So take that thought for a second about what we're going to do with the similarity transform. And this aside is going to be about what are called stream functions. Okay, and this should hopefully just finish us for the last 5 minutes. And we're going to need this to do the Blasi solution too. So we have this problem in that if we want to solve this equation, we've got Vx and Vy. So we have that relationship and we have the continuity equation that we have to kind of solve all together. And some smart people figured out a while ago that you could write things in terms of a stream function. Okay, and when you wrote something in terms of a stream function, that would allow you to simultaneously satisfy continuity. Okay, so basically, if we write our variables in a certain way, they'll automatically satisfy continuity. Okay, and so what people did is they defined the velocity as the cross product of some vector called psi, where psi vector is equal to 0, 0, minus not capital psi, so lowercase psi. So this is a capital psi and this is a lowercase. So hard to see, capital psi, this is a lowercase. Okay, and when you do this, if you plug this in here, what you'll find is that the velocity is equal to minus d psi dy in the x direction plus d psi dx in the y direction, or in other words, Vx is equal to minus d psi dy and Vy is equal to d psi dx. And we can verify that this is equal to, pardon me, or that if I put the continuity equation, if I do del dot V and I plug this in, I can verify that that's automatically 0. So there's 2 ways to do that. One way is I can plug this in. So if I do del cross psi and I put that in there, there's a vector identity that tells me that's identically 0. So that's one way to do it. Another way is to plug this definition in. That'll probably be more meaningful to you. I can do it's dvx dx plus dvy dy. So if I put the x derivative of minus d psi dy plus the y derivative of d psi dx, I get the second derivative crossed with respect to xy and the second derivative here with respect to cross sy, but this one's negative, so that gives me 0. Okay, so basically this trick here is a way to rewrite the velocities in terms of this stream function, but in a way that it always satisfies continuity. So I don't have to simultaneously solve these equations, okay? And notice that instead of having to solve for, Vy and Vx, now I could just solve for psi. And that takes care of the problem that Mark asked about when I have up here and I have Vx and Vy. So this is really great. This is a great way to solve problems. The bad part about it is it's only good for 2D. Okay, or for axisymmetric if you're in a different coordinate system. Okay, so like if you have, say, theta and phi, or r and theta, something like that. Okay, so you can't do it if you have a full 3-dimensional problem, but if you have something 2-dimensional, then it's great. Okay, and so this it automatically satisfies continuity. Okay, and you only have to solve one variable instead of 2. Okay, so when we pick up next time, what we're going to do is we're going to convert this guy into something that has a stream function. Okay, and we're going to do this rescaling, and that's going to lead to what's called the Blasius equation. And we'll do that, and we'll write out the Blasius equation, and then we'll solve it, and I'll show you the solution for a flat plate of boundary layers. Okay, so that's what we're going to do next time. That's all I've got for today. I'll take any questions you have, and then we'll head out. Okay. Thanks everybody for paying attention. I hope this was useful. And let me know, as always, if you have any questions about your project. Looks like you're about to say something, Zach.
I was just going to say thank you.
Okay. All right. Thank you. Okay. We'll see you later, guys.
Dr. Tree,
Yes.
I wanted to check if one of the papers that I found was reasonable for this project. Do you have office hours today, or can we talk about it right now?
We can just talk about it right now. We'll just let everybody kind of filter out unless anybody else has a question, then we can just chat for a couple of minutes.
Okay.
Let me hit stop recording here so that we can chat without